Electric motors provide the mechanical energy that's needed to operate a wide variety of equipment in industrial facilities. For example, pumps, fans, compressors, and motor-operated actuators typically depend on electric motors to function. An electric motor is a device that converts electrical energy into mechanical energy. This mechanical energy is in the form of a turning motion. The turning motion can be used to drive a load that is coupled to the motor. The turning motion is produced by the interaction of magnetic fields that are created in the motor. In fact, the movement of an object, such as the rotating part of a motor, as a result of the interaction between magnetic fields, is called motor action. To understand how electric motors operate, it's helpful to start with a simple example of how a magnetic field can be created. This illustration represents a section of wire with current flowing through it from negative to positive. The flow of current through the wire produces a magnetic field around the wire. The magnetic field consists of a series of lines known as magnetic lines of flux. All motors work because of the interaction of two or more separate magnetic fields. The interaction between the magnetic fields can be used to create rotary motion in a motor. We can use an illustration to see how this is done. In this illustration, a loop of wire is positioned in the magnetic field created by two permanent magnets. The loop is connected to a source of direct current, or DC power, which is not shown. Current flows from the negative side of the DC power source through the loop to the positive side. The current flow produces magnetic lines of flux that are perpendicular to the loop. As a result of the magnetic field around the loop, magnetic poles are created. In this case, the poles are perpendicular to the loop. The North Pole is here, and the South Pole is here. In order to show how the magnetic field around the loop interacts with the magnetic field of the permanent magnets, we'll represent the poles created by the loop with a simple bar magnet. The bar magnet is pivoted so that it is free to rotate. Now we can see that there is a pair of each type of magnetic pole in this situation. There are two north poles, which are next to each other, and two south poles, which are also next to each other. Like poles repel each other, so the interaction of the magnetic fields causes the bar magnet to rotate, and that's an example of motor action. As the bar magnet rotates, the repelling forces decrease because the like poles are getting farther apart. However, unlike poles attract each other. The bar magnet's north pole is attracted to this permanent magnet's south pole, and the bar magnet's south pole is attracted to this permanent magnet's north pole. The attracting forces increase as the unlike poles get closer to each other. So when the unlike magnetic poles are closest to each other, the attracting forces are the greatest. At this point, the bar magnet would stop rotating unless its momentum is great enough to carry it past the poles of the permanent magnet. This example illustrates only part of the rotary motion that's needed for a motor to operate. To keep the bar magnet rotating, the polarity of one of the magnets must be changed. Real motors use magnetic fields that change polarities to produce a continuous rotary motion. The way that this is done depends on the type of motor and whether it operates on alternating current or direct current. However, the basic principles that we've gone over here apply to all motors. A motor works because of the interaction of magnetic fields. In this simplified example, one field is produced by a bar magnet, and a second field is provided by two permanent magnets. The interaction between the two fields produces a turning motion. In other words, they cause the bar magnet to turn. However, the movement of the bar magnet would stop when its south pole is next to this permanent magnet's north pole, and its north pole is next to this permanent magnet's south pole, unless conditions change. One way to continue the bar magnet's rotation is to change the polarity of one set of magnetic poles. In an AC motor, this is accomplished using wires coiled around iron cores to form electromagnets. The electromagnets take the place of the permanent magnets used earlier. To explain how this works, we'll start with a single wire coiled around a single iron core. When current is supplied to the coil, magnetic flux lines are produced. When current flows through a wire that's shaped into a coil, the individual flux lines that are produced join together to create one large magnetic field. The core serves to concentrate this field so that it can have a maximum effect. Current flow through the coil creates a north pole and a south pole. Most AC motors have at least two coils in series. This illustration shows two coils around two iron cores. The two coils are connected in series. Alternating current, or AC, flows through the coils in one direction, and then reverses and flows in the opposite direction. As the direction of current flow alternates, the polarity of the coils changes. The alternating polarity can be used to produce continuous rotary motion in an AC motor. We can see how this works by adding a bar magnet between the two coils in our illustration. The bar magnet is the rotating part of the motor in this example. It's called the rotor. The two coils are the stationary part of the motor, which is known as the stator. Every AC motor, regardless of how it's designed, has a rotor and a stator. The rotor and the stator have magnetic fields that interact to produce continuous rotary motion. The like poles repel each other, so the rotor begins to rotate. The rotor's momentum and the attraction of its poles to the unlike stator poles also contribute to the rotation. As the rotor is turning, the current flow through the coils reverses direction, which causes the poles in the stator to reverse. So once again, the like poles are next to each other. The like poles repel each other, and the rotor continues to turn. As the rotor turns, the current flow reverses direction again, changing the polarities of the stator coils, and the rotor continues to turn. This cycle continually repeats, which results in continuous rotary motion. In this example, the stator has two coils of wire. These coils can also be referred to as poles, since they become north or south poles during normal motor operation. Keep in mind that the example of AC motor operation we've used has been simplified to help make things clear. For example, a motor with multiple poles works in much the same way as a motor with only two poles. Also, the rotor in an AC motor is some form of electromagnet rather than the bar magnet we used in our example.